In the previous video, we saw how we can define a pre-trained PyTorch ResNet 18 model for the task of multi-label classification. In this video, we will see how we can actually train it. Stay with me. Hello everyone and welcome to ML Done. Let's see how we can train our pre-trained ResNet model for the task of multi-label classification. We've already created the dataset class for where we can actually, split the data between train, validation, and test set. We can normalize it, and we've already also created our multi-label classifier based on the ResNet model. So first things first, we need to prepare the data. First of all, I'm going to define my image size. This is the size that I would like my dataset object to actually compress the original images to. Like if they're bigger, I want them to be compressed to this particular size. If they're smaller, it would upsample them to actually match this exact pixel size. Again, this is something that you can play with. But you should know that the lower this image size is, it means the more information you're losing, and it is more likely for your model to actually suffer for whatever task you're training it for, because it's losing information in the data. Now, if that is my image size, I'm going to create an object of my dataset class. I'm going to pass this to it so that it would tell it how it should either increase or decrease the size of the original images. The way I'll do that is, let's call this variable MLC dataset, and I'm going to create an object of my dataset class. And it's no mystery that the way you do that is you literally grab the name of your class, and you notice that the constructor, just as a reminder, is awaiting some image size dimension as a tuple. And that's what we're going to do. Upon creating this object, we will pass the image size as the input that it's actually awaiting. Once this object is created, as you remember, we can actually call this extra function that we have defined in it to actually split this data. So I'm just gonna say this MLC dataset object, I'm gonna call the train val test split on top of that. And just as a reminder again, this does not return anything. It internally splits the entire data into a train, validation, and test set. And that's it. Now let's run this. Great, now that is done. Now we know that this MLC dataset object already has the getItem dunder function inside of it. It means that once we actually start training our ResNet model or our multi-label classifier, we can actually, by setting the mode variable as we saw in the previous videos, we can dictate whether we want to access the training data for training the model, whether we want to have access to the validation data for validating the model, as well as whether we would like to have access to the test data for actually evaluating and testing the model. So this dunder function is going to be used in our data loader the second we start iterating through it. So we've already covered these main concepts in previous videos. So if you don't remember them, just check out the earlier videos in the playlist. Now, first and foremost, if we want to train a convolutional neural network in PyTorch, one thing that you should know is that you always have the ability to actually dictate what kind of processor you would like to train this model on, whether it's a CPU or it's a GPU, or if your laptop has, let's say, multiple GPUs, which one of those GPUs you would like the model to be trained on. That basically accelerates the speed. So I'm going to define my speed. On my local machine, I only have one GPU, and I would like to use that. The way you would define the device is through torch device, and inside, this is how you would say it. First of all, I'm going to say that, okay, look, I have my CUDA GPU, I have it, and I only have one, so I'm just going to say the 0th one, which is basically the only one and the only GPU that I have. I want you to use that as the device. Number two is I'm going to create a data loader. Again, like before, I passed the dataset object, the batch size, and I'm going to keep shuffling through. which means that after every epoch that I go through the entire data set for training my model, when the next epoch starts, I want to shuffle the entire data set before the next epoch starts. So that shuffling sort of habit is something that is really good practice in machine learning between every 2 consecutive epochs. It also makes sure that all of the data will be visited at least once, and it adds some variability to the training process with the hopes of finding the best trained model. I'm going to define my actual model. So I've already created the dataset class for my ResNet model, right? So I'm just going to put MLC, and remember that it awaits in the constructor the number of classes. So like any other object creation method, I'm just going to pass this, and let's say the number of classes, I'm just going to put this as number of classes, and we know that we have 10 classes here. So I'm going to pass number of classes here. So next is I'm going to put this model on my device. And it's pretty easy. You say model.to, and then you would pass your device variable. That's it. Now the model will be put on the GPU. I'm going to be defining the learning rate or the step size through using optimization. Because I'm going to be using Adam Optimizer. Adam typically is a kind of optimization algorithm that keeps your learning rate or your step size adaptive. It means that if the curvature on the error function or on the multidimensional error surface is really, really high, it means that you should be cautious in taking your steps. Otherwise, you might actually jump over the global minimum, or let's say a good local minimum. So if it's really steep, it would decrease your your step size, so that you would cautiously, with smaller step sizes, you would move towards hopefully a good minimum. However, if the curvature is really low, it means that you need to actually run faster. Otherwise, you will stay there forever. So it would increase your step size so that you would run. Also, it's good practice, and it has been seen in many experiments, that the initial learning rate that you would give as your initial step size to Adam better be really small, so that it has been shown that Adam works better if the initial learning rate is smaller. So I'm going to put the initial learning rate, just a number that I played with for some time, and it just worked really well. But then again, this is the kind of hyperparameter in a proper experiment design. You should try different varieties, of initial learning rates to make sure that you will find the best one. But here, for demonstration purposes, I'm just going to pick this very small learning rate. Next is the number of epochs. I'm going to just keep it at 10. And remember that every epoch is basically a whole sweep through the entire training data. It is important to know that here the training process is going to consist of training the entire multi-label classifier ResNet model. So even though we are using a pre-trained ResNet model, but note that I'm going to be training the entire network. Then you might ask them, why did you use a pre-trained model if you're going to, like overwrite all of those weights? The reason is because a pre-trained model has a better chance of reaching to an even better model for the task at hand, because those weights are not generated randomly. They have gone through hell to become what they are. They have been trained on the ImageNet dataset. It's an image dataset similar to the kind of dataset that we were working on. So there's a very high chance of those weights to be actually a good, incentive, a good sort of initial model for training the ResNet model for the multi-label classification dataset. That's really common in machine learning. Of course, the other approach is you would keep the pre-trained sort of portion fixed and frozen, and you would only train that final fully connected layer that we actually added in the previous video over here, which is randomly generated. The weights are randomly generated. You can keep everything fixed and only train the fully connected layer, but I doubt that you would get far with that. Now I'm going to define the optimizer. It's going to be Adam Optimizer. It would require me to pass the parameters of the model that we would like it to actually keep track of and update during the training process. And it's really easy to tell this to tell Adam, consider all the parameters in my model. So you can just say literally model dot parameters. This literally returns the entire parameters in the ResNet model. And of course, the initial learning rate is going to be my eta. And again, remember that I'm saying initial learning rate because this will change during the optimization process. One last thing is that I want to keep track of the loss that I'm going to be defining very soon. I'm going to keep track of the loss at the end of every epoch. So I'm going to define a list that will basically, I will append these losses per epoch into it. So let's call it epoch train loss as an empty list. Last but not least, before actually creating the loop of going through the entire data, because remember, because I'm just going to train my model, I'm only going to need the training portion of my dataset class, right? So I'm going to set the mode, the instance mode variable inside my dataset object to train, so that only the training portion will be passed through the iteration, right? And also, if I'm interested in the length of my object, only the length of my xtrain will be returned. Okay, so that was the smart move that we made in one of the earlier videos. So again, it's very simple. I'm just going to say the MLC underscore dataset mode equals train. And that's it. Okay, now we're going to run the cell. All is good. Now, lo and behold, we're going to start the iteration through the entire data set or the training set. Let's say for epoch in range number of epochs. First of all, I'm just going to define a sort of list here that I'm going to be emptying. I'm defining it at the beginning of every epoch. So you'll see why I'm defining this. This is different to the epoch train loss that we've defined before. Next, because I want to train my model, I have to put it in train mode. Okay, model.train. You can also do it up there, like up here. You don't have to keep setting this to train every time. The reason I put it here in the for loop is because later on I'll show you how to actually validate the model as well. So we will keep alternating between train and validation mode of the model throughout every epoch. So I'm just going to keep it here, but if you're only going to do training, you should actually put it up there over here. I'm going to be using my data loader here. So for D in my data loader, first foremost, you have to set the gradients to 0 every time you want to go through the entire data set. It's very important because at the end, so every time an input data is passed through your ResNet model, the gradients are calculated. The gradients of the error with respect to the weights of your model are calculated, and then you will use your optimizer to actually update the parameters. But before visiting the next data point, you want to make sure that you will clear everything, start off with a clean slate before the next data point comes in, just to make sure the gradients will not be overwritten or will not be added on top of each other, because that could make an entire mess. So you would see this line a lot in PyTorch, that you would always say optimizer 0 grad before visiting every data point. Next, note that every time we iterate through the data loader, because we've set the mode of the dataset to train, every time the getItem function will be called inside the dataset class. And because self-mode is train, every time this capital D becomes this entire dictionary, basically. This will be returned. So the keys are images and labels, and the values are the exact image in the xtrain that lives on the index IDX, and the corresponding label that lives in y underscore train in the index IDX. Okay, so it's important to note what we're dealing with here. This capital D becomes that dictionary. So if you want to access the image and the label, you need those keys in that dictionary to actually grab them. So let's say data is equal to the images, right? You have to put this data on the same device that your model is on. That's very important. Otherwise, you would get this error from PyTorch that your model is, let's say, on GPU 1 and your data is on CPU. We can't work together. You have to put them on the same device. And that is why you would put this on device. Again, very similar to the way that you would put your model on your device. One last thing here that's usually important is that I'm always in the habit of making sure that my data is in the correct format, correct torch format. The weights in your ResNet model, they are of the type torch.cuda.float tensor. They're float tensors, and sometimes when you sort of convert your, let's say, images in Python to NumPy arrays, and then you want to convert them into torch tensors, sometimes throughout all of those conversions, the data type will not be the final data type will not be torch CUDA float tensor. And for example, in this case, if I don't do what I'm going to do now, the type of data is going to be torch CUDA double tensor. And because this double tensor has to travel through the ResNet model and all the weights are of the type float tensor, the multiplication and the math will not work. They need to be of the same exact type. That is why I'm gonna also pass this argument here that says d type equals torch float, okay? And the same logic, I'm gonna grab the labels as well using the labels key. I'm gonna put it on device, and again, I will pass the data type as torch.float. Next, this is the interesting part. This is actually the forward pass. You have the data. You need it to travel through the entire model. The output will be produced. You will compare that output with the ground truth that is now saved in labels. The gap between the two is your error. So you calculate that error. Next, you will calculate the gradient of that error with respect to each and every one of the weights in the entire model. Then you update all of those parameters using your optimizer. And then the next input data will be visited. So this will happen at every iteration of this for loop. And after all the data has been observed and all the gradients have been calculated and all the parameters have been updated one by one, then we go to the next epoch where everything will be shuffled, right? And then again, the entire data set the entire training set will be visited, and again, the same thing keeps happening and happening for the number of epochs that we have. So how do we actually do the forward pass? This is the easy part. Like y hat, which is the outputs of the model, you literally just pass your data like that to the model. This is your ResNet model. And that's it. It generates the y hat, which is the outputs of your model. And this is where you have to compare this y hat with the actual ground truth labels. How do you define the error? Now, this is a very, very important sort of aspect of multi-label classification that I want to hit home. We've seen in earlier videos that the way you would define these multi-label classification neural networks is that if you have 10 class labels, you would have 10 neurons, but the output function is going to be one sigmoid function per output unit. It's not going to be one softmax for the entire 10 outputs where the sum of the outputs will always be 1. It's not a multi-class classification, it's a multi-label classification. So you would have a sigmoid unit defined for each one of the output neurons. And we've seen how we do that and how we define the gradients and outputs for multi-label classification in the earlier videos. You might also notice that in the forward pass, there's no sigmoid function here, right? We haven't defined that. Then you would say, okay, you said we need a sigmoid function, then where the hell is it? And this is where I'm going to actually put the sigmoid function. There is a kind of binary cross-entropy loss function that has a sigmoid functionality inside of it, which means that it grabs the y-hat, the predictions, it applies a sigmoid on top of it, and then compares the result with the ground truth. Right, so now let me define my error as from the nn torch.nn module. I'm going to define as nn BCE. So it's BCE, not BCE loss, but BCE with logit loss. This is the one that applies sigmoid before actually computing the binary cross entropy error. And in order to actually apply that to the ground truth and y-hat, you would first pass y-hat and then you would pass the ground truth. That's it, right? First the predictions and then the ground truth. And because this results in, like if you have 10 outputs, it will result in 10 different values, like 10 values for the y-hat and 10 values for the ground truth. If you calculate binary cross entropy between each two pairs, you would end up with a vector of size 10. So you need to aggregate all of these 10 values in one way or the other, either average them or sum them. That's in your control. What I'm going to do is I'm going to sum them. So this entire thing, the output, I'm going to put it in torch.sum. And then this will be my loss. Right? And as we saw, once you calculate the loss, that's when you have to start calculating the gradients through the entire computational graph. Now, again, another beauty of PyTorch is that calculating the gradients is as simple as this. Loss.backward. With one line, you calculate the gradient of your loss with respect to all of the parameters in your model. And then the question is, okay, you've calculated these gradients. How will you incorporate those gradients into the current values of your parameters in your model and update all of them? That incorporation of how the gradients will affect the weights, which is basically training your model, that is what the optimization algorithm will dictate. I'm going to be using Adam, right? So all you need to do is you just call the step function of your optimizer, and it does that automatically, as simple as that. I just want to make sure that I will keep keep a record of this loss before I actually visit the next data point. And that is why I have this train losses list. I'm going to be putting the actual value of the loss, and it's a torch tensor. So the way if you have a scalar torch tensor with just one value, you can just call the item method to actually grab that one value. I'm going to put it in losses, and that's it. So after this loop is done, you will have visited the entire training set. You will have calculated the gradients and updated your weights. After having visited the entire training set, and that would be your first epoch. Okay, now before going to the next epoch, I also want to keep a track of my epoch losses, and that is when the epoch list that I created up there is gonna come in handy. I'm just gonna put there, and then I'm gonna take an average of train losses, right? So I just literally, I'm gonna use my numpy here, append, numpy mean, and then I'm going to be passing my train losses here. You might ask, why am I using numpy here and not torch? You can, but the problem is torch has a problem with because train losses is a list of tensors. Torch has a problem with dealing with lists. You need to convert the list into a sort of torch tensor, and it's just a little bit of hassle. So I'm just being lazy here. NumPy doesn't give you that much of a problem. It just takes an average. It doesn't mind the fact that you have a list of tensors here. It would just do it seamlessly. And last but not least, before going to the next epoch, I just want to have some print messages here, so we know which epoch we are at, and at the end of every epoch, what our loss is, right? So it's easy, like train epoch and then train loss. The format is going to be with 6 decimal points, and then we have epoch plus 1. Well, because epoch starts with 0, we're using Python, and that's always the case. So I'm just going to put a +1 here, and then I'm going to take an average, again using NumPy, of train losses. It's going to be the representative of how well my model has done during the current epoch. Remember that because we are dealing with a big ResNet model, every epoch might take some time, and that is basically why I set the number of epochs to 10 rather than a huge value, because it will take time. So let's run this. Yeah, so as I said, it's taking some time. So the first epoch, that's our loss, 0.17. For the second epoch, it's going down. So that's what you'd like to see. Like, you would like to see the training loss keep going down and down and down, and that's exactly what's happening. So let me just speed up the process. Okay, great. So now we see that the loss is going down at the end of every epoch, and that's good news. And also, if you want to visually see it, it's pretty easy. You could plt.plot epoch train losses. I'm going to put a label train loss, and then let's say the color is red. Let me just make sure that by plt.legend that label will be shown, and then even let's get a little bit fancy, make sure that the plot has a grid, and then you have to obviously call show to actually see how the training loss looks like, which is good. So you see that we have already 10 epochs here on the x-axis, and the loss is continuously going down. Of course, there's always a problem of overfitting, and that's why we have a validation set in our dataset class to make sure that we will not overtrain our model, and we will find the sweet spot that where the training error keeps going down, but the validation set all of a sudden starts shooting up. In the next video, we'll see how we can actually use a validation set to make sure that we will not overfit the data. If this video was useful, feel free to give it a thumbs up. It will help with the algorithm immensely. And if you have any questions, feel free to post them in the comment section down below. I always appreciate it. And share the video if you liked it. Thank you very much.